In this video, we will see about the level order traversal of the tree. Now, what is level of order traversal of the tree? That means you have to traverse the tree level by level. And what is a level? Set of all nodes at a particular depth is called as a level. And for this, we will use a queue data structure over there. And why we need a queue, I will explain you it in some time. And what we store it in queue, that is very interesting question, and we will see what to store it in queue. But before that, we will see what is the level order traversal of this tree. Level order traversal of this tree is 10. Next you get 8. Next you get 25. Next is 5, 9 and 6. Level by level you print it. Right. Now, how we solve this? Let us see how do we use a queue data structure over here. We solve this level order traversal using the queue data structure. Right. Now, we take the linked queue over here. Okay. What is the first step? We enqueue the root onto the queue. Now the question comes, what is root? Root is 9000. But the root's data is 10. Right. Why we enqueue the root 9000, that is the address, why not 10? That's the question that I will answer in some time. Therefore, we take the queue using the linked list, and what do I enqueue over here? I enqueue the root which is 9000. Let me write the algorithm over there. I say enqueue in queue. What do I enqueue? I enqueue the root. And what is the value of root? The value of root is 9000 and 9000 is enqueued on the queue. Right. It means what we store on the queue? We store address of a node on queue. What do we store? We store address of a node in queue. We store address of a node onto the queue data structure. Now what we do, till this queue becomes empty, we start deleting one by one element from there. Hence I write while queue is not empty. This is the algorithm that I am writing. Yes, queue is not empty. Therefore, we delete the front end of the queue. Now, when I say dequeue from the queue, what do I get when I dequeue? I get the front end of the queue. And what is the front end of the queue? 9000. And what is 9000? The address of the node. Therefore, I store it in some variable p. And what should be p of type? P should be of type struct node star, because when you dequeue you get 9000. Right, you dequeue it, you get 9000. Now the value of p over here is 9000. Now from this 9000 I can get 9000 arrow data which is 10. That is what I want to print. Therefore I say over here printf %d p arrow data. That is 9000 arrow data. And what is 9000 arrow data over here? It is 10. Right. Now from 10 you could not have got 8. Right. Because 10 is a data. But from p, which is 9000, you can get the address of this node. What is the address of this node? It is 2000. How do you get it? You say 9000 arrow left. 9000 arrow left is 2000 and 9000 arrow right is what? 3000. That is what we do over here. Therefore, we say p arrow left and p arrow right. Now, this 9000 arrow left, which is 2000, should be enqueued on the queue. Hence, we write over here enqueue. In the queue, what do we enqueue? We enqueue p arrow left. Now, what is p arrow left? 9000 arrow left is 2000, and this 2000 is again an address of the node. Therefore, you enqueue 2000 onto the queue. Right. The next thing is you take the right child of it. Now, how do you get the right child? You say enqueue &q p arrow right. Now, why we enqueue the left child first and then the right child? Because we need from left to right. We are traversing from the left to right. Therefore, first left child, then the right child. Now, what is the right child? It is 3000, and 3000 will be added to the rear end of the linked queue. Added. Go back again, queue is not empty. Yes, queue is not empty. You say p is equal to dq. And what do you get from the dq? You get this 2000 from the dq. This is being removed. Yes. Now you say printf 2000 arrow data. What is 2000 arrow data? 8. 8 is printed. Now enqueue P arrow left, 2000 arrow left. What is 2000 arrow left? Here it is 4000. Therefore you enqueue 4000 over here. Now enqueue P arrow right, 2000 arrow right. What is 2000 arrow right? It is 5000. 5000 is being added at the rear end of the queue. Now this is the queue that we have from front to rear. Now again you go back, Q is not empty, SQ is not empty, P is equal to DQ. What do you get from DQ? You get 3000 from DQ, yes? You get 3000 from DQ. You print 3000 arrow data. And what is 3000 arrow data over here? It is 25. 25 is printed. Now you say enqueue P arrow left. What is P arrow left over here? 3000 arrow left is null. Now, is it necessary to write null into the queue? There is no necessary, because you don't print null. You don't print null arrow data because that's segmentation fault. Therefore, I have to enqueue only if P arrow left is not equal to null. Now, what is 3000 arrow left? Null. Null not equal, null is false. Similarly, what is 3000 arrow right? It is null. Is it necessary to enqueue null over there? No. Therefore, I enqueue only if P arrow right is not equal to null. Now, what is P arrow right? 3000 arrow right is null. Null not equal, null is false. Go back. Q is not empty. Yes. P is equal to DQ. And what do you DQ from the Q? You get 4000 from the Q. Okay, now you print 4000 arrow data. Now what is 4000 arrow data? It is 5. P arrow left. What is 4000 arrow left? Null. Null not equal, null is false. Do not enqueue. P arrow right. What is 4000 arrow right? 6000. Not equal to null? Yes, not equal to null. Therefore, enqueue 6000 onto the queue. Now this is the queue where I am enqueuing what? 6000 over there. Go back, Q is not empty. Yes, P is equal to DQ. What do you get? You get 5000. That means this is being removed. Now, you say printf 5000 arrow data. What is 5000 arrow data over here? 9. Now, what is 5000 arrow left? 5000 arrow left is null. Null not equal, null is false. Do not enqueue. 5000 arrow right is null. Null not equal, null is false. Do not enqueue. Go back. Q is not empty. Yes, Q is not empty. Again, you say P is equal to DQ. What do you get? You get 6000. Print 6000 arrow data. What is 6000 arrow data? 6. 6000 arrow left is null. Null not equal, null is false. Do not enqueue. 6000 arrow right is null. Null not equal, null is false. Do not enqueue. Again go back. Q is empty. Q not empty is false. You come out and you see that the level order traversal of the tree is being done. And this is the algorithm. And again, what we are storing in the queue? We are storing address of a node in a queue. And this queue we are implementing using what? We are implementing using linked list, that is linked queue. Therefore, I need a node. I need a node, right? I need a node for the queue. How do I write node for the queue? If I say struct node, this node name is already taken for the binary search tree. Therefore, I cannot use the same name. Instead of node, what do I say? I give some different name and I say node with respect to queue. Right, I cannot take node name, it is just the name change. Why you cannot take node name? Because node name is already taken for binary search tree. And in this node of the queue, what we are doing? We are storing two things. Here I am storing the address. Now this address becomes what? The data part of it. Now this data, and the second thing what you have in the node is what? The next pointer. Therefore I write over here star next. Now, what does this next pointer is doing? It is holding the address of its own node. That means it is holding the address of what? Struct node queue. Right? And what is data? Data is 9000. 9000 is nothing but a pointer. Pointer to what? Pointer to the node of the binary search tree. And what did we write over here? Struct node star data. This is how the structured definition of the node queue will look like. Now, after we see the structured definition of the node queue, let us see how do we define the queue over there. How do we define? We say struct queue. Okay. Now, this queue is made up of what? Linked list. Here I write it. Suppose I say 5000 and here I write 7,000. Example. Now, this is the front end of the queue, this is the rear end of the queue. That means I need two pointers. One is front and one is rear. Therefore, I write over here star front. And next one, what do I write over here is what? Star rear. I need two pointers. Now, this front is a pointer to this node. Agreed? Now, what is this node? In this node, we are storing address of a node as well as pointer to the next node. That means it is a node queue, right? It is a node queue. Therefore, this should be of what type? Struct node queue star front. And what do I write over here? Struct node queue star rear. Why I did not use node over here? Because that name is already been taken for the binary search tree, right? Now, after we define the node and all, see over here. Now, I want to write the enqueue function and the dequeue function. Now, how do we write the enqueue function? We say void enqueue. Okay. Now, to enqueue, the first parameter is always the queue. I say struct queue star queue. And the second parameter is data, that is E. Now, what I am saying over here, P arrow left. I would have written over here something called as enqueue ampersand q comma root. Right, I would have written. Now, what is root of type? Struct node star. Right, and I said in queue we are storing address of a node. Therefore, this E should be of what type? Struct node star. Right, now the question comes, how do we write the enqueue function so that we add at the rear end of the queue? That already I have done it. The same thing I am going to do again. Now, the first thing is we have to create a node. Now, the question comes, node should be of what type? Node should be of what type? Node queue type, because we are storing node queue over here. Therefore, I say struct node queue star p is equal to struct node queue star malloc of size of struct node queue. Right. Now, if suppose the memory is full, the value of p would be what? Null. That is what I am going to write. If p is equal null, then we say printf memory full and we return back, or you say queue is full and we return back. If suppose the queue is not full, now if queue is not full, what will happen? Memory has to be created. Therefore, a memory would be created over here. Suppose this is P. Let the address of this be say 33,000. Now, there are two things in P because it is node queue. It is not node where there were three things. It is node queue, two things, data and next. And what do we write over here? We say P arrow data is equal to E and P arrow next is equal to null. Suppose I say E is 9,000, that is the address, and P arrow next is null. Are we adding this node for the first time? Yes. How do we know if the value of front and the value of rear is what? Null. That we have to do in initQ function, and hence I write if Q arrow front is equal Q arrow is equal null. That means we are adding it for the first time. Then what do I write over here? Q arrow front is equal Q arrow rear is equal P. That means this becomes the front end of the queue and this becomes the rear end of the queue. Next time if I say again enqueue, you say P is equal to malloc. This is P is equal to malloc. Data, you write some data and the next pointer is null. Right. Is Q arrow front equal to null? No, that means we are not adding for the first time. Therefore, we say else. And what do I say? Rear arrow next. Why rear arrow next? Because you are adding at the rear end of the queue. Hence I say Q arrow rear. Now when I say Q arrow rear, this complete node is taken and I need the next pointer over here. Hence I say arrow next is equal to P. This is being established and this should become the rear end of the queue. Therefore we say Q arrow rear is equal to P and this becomes the rear end of the queue, and you see that the node is being enqueued at the rear end of the queue. This is how we write the enqueue function. Now let us see how do we write the dequeue function. Now whenever you dequeue, what do you get? You get 9,000, and that 9,000 is what? struct node star. And what do I write over here? DQ, and here I say struct Q star Q. Right. Now, how do you DQ from the rear end of the queue? We take one pointer over here. We DQ from the front end of the queue. I'm sorry. Now, this P should be pointing to the front end of the queue, and front is of what type? Struct node Q star. Therefore, I take one pointer. Struct node Q star P is equal to Q arrow front. Right. This is where I get it. Now, I want to delete this node, that means front should go ahead. And how do I write it? Q arrow front is equal to P arrow next. This is where the front end of the queue will go to. Now, I don't need this node. Before I delete this, I want to store the data. Now, what is the data over here? 9000. Data is of what type? Struct node star. Therefore, I say struct node star E is equal to P arrow data. That means the value of E will be 9000. I don't need this node. Therefore, what do we say? Free P. That means this node is being gone. Right. And at the end, answer is stored where? Answer is stored in E. Therefore, what do I write over here? Return E. I hope that you have copied down this. I erase this. And here I say return E. That means 9000 will be done. Now, if I want to delete it again, you say P is equal to Q arrow front. This is P. Q arrow front is P arrow next. What is P arrow next over here? Null. That means the value of front would be null. E is P arrow data. What is P arrow data? Whatever is the data. Free P. That means this will be gone. Now, where rear is pointing to the freed location. That means the value of rear also should become null. If the value of front is equal null, then what do we say? We say that the value of rear is also null. This is how we write the DQ function. Now, let us see how do we write the initQ function. How do we write it? We say void initQ struct Q star Q. And what do we write over here? We say Q arrow front is equal Q arrow rear is equal. Now, this is how I write the enqueue, DQ, right? The structure definition of queue, the structure definition of node queue was there, and the initQ function. Please copy down this. Then we will see how do we write the program for the level order traversal of the tree, because I need all those things over there. Thank you. Let us write the code for it. That is case 5. And we will write one function called as level order, and we know that the root doesn't change, and whenever root doesn't change it has to be passed by value. Therefore we say root, and this is the end of the case 5. Now, how do we write the level order traversal of the tree? We say void. What is the function name? Level order. What is the first parameter? Root. Root is of what type? Struct node star root. Now, to do this level order traversal, again, if the value of what? Root is null, can we do it? No. Therefore, we say over here, if the value of root is null, that means nothing to be done, nothing to be displayed, because the root itself is empty. Hence, I say return. If the root is not null, then what we do? We create a queue. And already I have written the function for queue. Hence, I say struct queue and queue. Now a queue will be created. What is there in queue? There are two things. One is the front pointer and one is the rear pointer. This is queue. I have defined the queue. See over there. And the front pointer and rear pointer should be made as what? Null. Therefore, for this we will write one function called as initQ ampersand queue. Now what will happen? The front end of the queue and the rear end of the queue will be null. Now what you need to do? You need to enqueue root to the queue. And how do you do it? We have written one function called as enqueue. You say ampersand queue comma root. Now what is the value of root? I remove this as of now. What is the value of root? The value of root is 9000. 9000 is being written at the front end of the queue. This is front and this is rear. Right. Now the enqueue is done. Till the queue is not empty, I have to start the procedure. Therefore, I write over here while not is empty of queue. Now, I have not written the function is empty. You have to write it yourself. It's very simple. If queue arrow front is equal null, that means the queue is empty. Yes, the queue is not empty. You have to dequeue an element from the front end of the queue. I say dequeue of ampersand queue. Now when I say dequeue of ampersand queue, what do I get? I get 9000. That means this is the address of a node. Now therefore I say struct node star p. P is equal to dequeue. Now what will be the value of p? The value of p would be 9000. Right. Now you have to print the 9000 arrow data. You say printf %d comma p arrow data. Now what is p arrow data? P arrow data is 9000 arrow data is 10. 10 is being displayed. Now you check whether 9000 has left child, then enqueue. Whether 9000 has right child, then enqueue. That is what we write. If p arrow left not equal to null. Now what is p? 9000 arrow left is not equal to null. Yes, then we say enqueue. What do you want to enqueue? We want to enqueue p arrow left. Now what is p arrow left? P arrow left is 2000. 2000 is being added to the rear end of the queue. Similarly, you check if p arrow right not equal to null, then what do we say? We say enqueue ampersand q p arrow right. Now what is p arrow right? P arrow right is 3000 is being enqueued over here. Again go not is empty of q. Yes, p is equal to dq. That means you get 2000. You print 2000 arrow data, that is 8. Again you check 2000 arrow left not equal to null. Yes, therefore you enqueue 4000 over here. 2000 arrow right not equal to null. Yes, you enqueue 5000 over here. Right, again go back, not is empty of q. Yes, p is equal to dq. What do you get? You get 3000 from the front end of the queue. Print 3000 arrow data. What is 3000 arrow data? 25. 25 is being printed. Now p arrow left. What is 3000 arrow left? Null. Null not equal null is false. Do not enqueue it. 3000 arrow right is 6000 not equal to null. Yes, you enqueue 6000 at the rear end of the queue. Go back. Q is not empty. Yes, p is equal to dq. What do you dq? You dq 4000. Print 4000 arrow data. What is 4000 arrow data? It is 5. Now 4000 arrow left is null. Null not equal null is false. 4000 arrow right is not equal to null. Yes, therefore you enqueue. What do you enqueue? You enqueue 7000 at the rear end of the queue. Again you say p is equal to dq. What do you dq? You dq 5000. Print 5000 arrow data. What is 5000 arrow data? 9. 9 is being printed. 5000 arrow left is null. Null not equal null is false. 5000 arrow right is null. Null not equal null is false. Therefore do not enqueue anything. Go back. Q is not empty. Yes, p is equal to dq. What do you dq? You dq 6000 from the queue. Print 6000 arrow data. What is 6000 arrow data? It is 37. 6000 arrow left is null. Null not equal null is false. 6000 arrow right is null. Null not equal null is false. Go back. Q is not empty. Yes, p is equal to dq. What do you dq? You dq 7000. Print 7000 arrow data. What is 7000 arrow data? 6. 7000 arrow left is null. Null not equal null is false. 7000 arrow right is null. Null not equal null is false. Go back. Q is not empty. The condition fails and you come out and you see that the level order traversal of the tree is being printed. And in the next video we will see how do we find the height of the tree and how do we count the number of nodes as well as the leaf nodes, and that would complete the program on the binary search tree. Thank you. Let us now see how do we find the height of the tree. Now what is the height of the tree? It means the number of levels, that is the height of the tree, or the number of nodes from root to the deepest node. Now what is the deepest node? It is 7. 1, 2, 3, 4, 5. The height of this tree is 5. That means the deepest node can be on the LHS or the deepest node can be on the RHS subtree. We don't know. It means what is the height of the tree? It is the maximum of the number of nodes on the left side or the number of nodes on the right side, including the node itself. Therefore I say plus 1. Why plus 1? Because what is the depth of the node on LHS of 25? It is 1, 2, 3, 4. Therefore I say max of 4. 4 on LHS. What is the depth on RHS? 1, 2. 2 on RHS plus 1 plus this node as well. Therefore, max of 4 and 2 is 4. 4 plus 1 is 5. Therefore, the height of this tree is 5. Now the question comes, how do we find the maximum of the height on the LHS subtree and RHS subtree? Now if I say what is the height on the LHS side, do I know what is the height on LHS side? No, I have to go on LHS. I want to find the height on LHS with respect to 10. Do I know how many nodes are there with respect to 10 on LHS? No. Again I go on LHS. Do I know how many nodes are there with respect to 7 on LHS? No. Again I go, when I find the leaf node, I say 0 number of nodes are there on LHS with respect to 7. Similarly, 0 number of nodes are there with respect to 7 on RHS. That means what is the first computed node? The first computed node is 7. Now, again I come over here. I want the number of nodes on the RHS. Do I know how many number of nodes are there on RHS? No. Again I come over here. Again over here, again over here. Now when I come over here, the number of nodes on LHS is 0, RHS is 0, and the second computed node is 16. That means first you compute the LHS, next you compute the RHS, next you compute the node. Now which order traversal it is? It is the post order traversal of the tree, because it is left, right and root. Remember, whenever you find any question on the tree, majority of the question can be solved with any one of the 4 traversal. Either it is in order, pre-order, post order or level order. And if I want to use recursion over here, the post order traversal of the tree suits. It can also be done using level order traversal, that I leave it as an assignment. Now what is the answer for this, the height of the tree? It says 5, it says 0, it says 2. That means integer is the answer. Hence I say case 6, it is the height of the tree. We say height of root. Why we say root? Because height of the tree is nothing but height of the root. It returns some answer. Let us store it in h, and you say print h. That's the height of the tree. Now let us write the function height. We say int. What is the function name? Height. What is the first parameter? The first parameter is struct node star root. Now, suppose the value of root is null. If the value of root is null, tree is empty, can there be any height over there? No, it is 0. Therefore, we say if root is equal null, then what do I write over here? Return 0, because there is no height, and this also forms the base condition over there. Now, the next thing is I need to travel the tree in the post order fashion. Now what is post order fashion? We say height of, first on the root arrow left, we say root arrow left. Now this will return integer, the height function. It has to be stored in some variable. Let us store it in some variable called as L, represents the left height. Then you have to compute the right height. What do I write over here? Height of root arrow right. Now again height function returns integer. I have to store it in some variable. Let us store it in R. Now what to do later, we will see it in some time. Now let this be the line number 1, 2, 3, 4 and let this be the line number 5. Now we call the function height of root. Of course root is a address, but as of now I just take, let 25 itself be the root. Yes, 25 is root. Is root equal null? No. Now how many local variables are there? There are 2 local variables, L and R. Now you call the function height of root arrow left from line number 3. Height of root arrow left, 25 arrow left is what? 10, and we are calling this from line number 3. Again there are 2 local variables, left and right. Go back, 10 equal null? No. Again you say root arrow left. Again we write over here height of root arrow left, that is 7. Again we have 2 variables left and right, and we have called this function from line number 3. Go back. Is 7 equal null? No. Again you execute line number 3 and we say height of 7 arrow left. What is 7 arrow left? Null. And we have called this from line number 3. See here, 7 arrow left is null. Now again go back. Root equal null? Yes. You return 0. Where do you return 0? To line number 3. That means left height with respect to 7 is 0. That means the number of nodes on the LHS of 7 are what? 0. Now you have to compute the number. Number of nodes on the RHS of 7. Line number 3 is done. Now you execute line number 4. It says height of root arrow right. Now what is root arrow right? 7 arrow right is null and the return line number is 4. Root equal null, yes. You return 0. Where do you return 0? To line number 4. That means the right height with respect to 7 is what? 0. Are you getting it? Now, the left height with respect to 7 is 0, right height with respect to 7 is 0. You have to see which one is maximum, because the maximum depth or the maximum number of nodes might be on LHS or might be on RHS. That was what I write it. If L is greater than R, then we say return 1 plus L. Why 1 plus? Because you have to count that node itself. Else, what do we write over here? Return 1 plus R if R is greater. Now what is the value of L? 0. What is the value of R? 0. 0 greater than 0 is false. Return 1 plus R. 1 plus R is what? 1. It returns 1. Where does it returns 1? To line number 3. Therefore you say L is 1. That means the LHS height with respect to 10 is what? 1. Now you have to compute with respect to RHS. Again you call the function height of root arrow right. Now what is 10 arrow right? 10 arrow right is 15 and the return line number is 4. Again there are two variables L and R. Is 15 equal null? No. Again you call the function height of 15 arrow left. Now what is 15 arrow left over here? It is null and we are calling this function from line number 3. Null equal null? Yes, you return 0. Where do you return 0? To line number 3. That means left height with respect to 15 is what? 0. You have to compute the right height now. Now how do you compute the right height? You say height of 15 arrow right. What is 15 arrow right? 17 and the return line number is 4. Again we have two variables left and right. Is 17 equal null? No. Again you say 17 arrow left. What is 17 arrow left over here? It is 16 and we are calling from line number 3. This is left and this is right. Is 16 equal null? No. Again you say 16 arrow left. Now what is 16 arrow left? 16 arrow left is null and you are calling this from line number 3. Null equal null, yes. You return 0. Now where do you return 0? To line number 3. That means left height with respect to 16 is what? 0. Next you execute line number 4. You say 16 arrow right. And what is 16 arrow right again? It is null. You are calling this from line number 4. Is null equal null? Yes. You return 0. Where do you return 0? To line number 4. Line number 4 says R equal to 0. That means right height with respect to 16 is 0. Next you compute line number 5. 0 greater than 0 is false. Return 1 plus R. 1 plus R is what? 1. Where do you return 1? You return 1 to line number 3 of 17. Now line number 3 says L equal to 1 and it says left height with respect to 17 is 1. Now you have to compute the right height. Execute line number 4. Height of 17 arrow right is null. Return line number is 4. Null equal null is true. You return 0 to line number 4. That means the right height with respect to 17 is what? 0. 1 greater than 0? Yes, 1 is greater than 0. Return 1 plus L. See here. 1 is greater than 0. Yes, 1 is greater than 0. Return 1 plus L. 1 plus 1 is what? 2. Where do you return to? To line number 4. Therefore, I write over here R is equal to 2. That means with respect to 15, the right height is 2. Done. Now execute line number 5. L is 0, R is 2. 0 greater than 2 is false. Return 1 plus R. That is 1 plus 2. What is 1 plus 2? 3. Where do you return 3? To line number 4. Therefore, you say R is equal to 3. That means the right height with respect to 10 is 3. Now, line number 4 is done. Execute line number 5. 1 and 3. 1 greater than 3 is false. Return 1 plus 3. And what is 1 plus 3? 1 plus 3 is 4. Where do you return 4? To line number 3. It means at 25, the left height is 4. Right? The left height is 4. 1, 2, 3, 4. Left height is 4. Now you have to compute the right height. Now execute line number 4. It says height of root arrow right. 25 arrow right. What is 25 arrow right? 37. Let me take this note so that the tracing becomes very simple. 37. Now what is the return line number? Return line number is 4. This is left and this is right. Go back. Is 37 equal null? No. Again you say 37 arrow left. Now what is 37 arrow left? 37 arrow left is null. Return line number is 3. Null equal null? Yes, you return 0. Where do you return 0? To line number 3 and you say left height is 0. And you execute line number 4, 37 arrow right is again null, return line number is 4 because 37 arrow right is null. Go back, null equal null, yes, return 0. Where do you return 0? To line number 4. Now execute line number 5. 0 greater than 0 is false. Return 1 plus r. What is 1 plus r? 1 plus 0 is 1. Where do you return 1? To line number 4. Therefore, you say right height is 1. Now, you have to execute line number 5. You have to take what is maximum? 4 greater than 1. Yes, 4 is greater than 1 because L is 4, R is 1. Therefore, you return 1 plus L. What is 1 plus L? 1 plus 4 is 5. And you say the height of this tree is 5. It's very simple. If root is null, you return 0. Else you find the height of left subtree. You find the height of right subtree. You pick the maximum out of it. And you say 1 plus the maximum out of it. And this can be also written as in books and all. You see int height, struct node star root, and they have written if root equal null, then we say return 0, else they will write return maximum of height of root arrow left, comma height of root arrow right plus 1. This is the other way of writing it. Now what we have done, we have taken root arrow left in L, root arrow right in R, and we have computed the maximum of these things, right? Maximum of L comma R is whatever it is, and we have added 1 to it. This is the other way of writing it, and you will see in majority of the book. But in order to understand for you, I have written in a very easy manner. This is how the height of the tree is computed. Now let us see how do we compute the number of nodes in a binary tree. Thank you. Let us see how do we count the number of nodes, that is the size of the tree. How many number of nodes are there? 1, 2, 3, 4 and 5. Now if I do in order traversal, I visit every node. Right, because what is in order traversal? 7, 10, 11, 25, 37. Post order, you visit every node. Level order, you visit every node. Pre-order, you visit every node. That means you can use any traversal over here. Now, how do we write it? I say case 8, the number of nodes. It gives the answer as 0, 5, 10, 100 or something. Let us store it in Y. And I say we will write one function called as count nodes. And I need the root of the binary tree, and this root does not change, and at the end you print the value of y. This will end the case 8. Now how do I write it? I say int, what is the function name? The function name is count nodes. What is the first parameter? Struct node star root. Okay, now if the value of root is null, right, what does it mean? There are no nodes. And if there are no nodes, what should be the answer? The answer should be 0. Therefore, we say if root equal null, and I write over here return 0. And this is the base condition of this recursion as well. Now, what are the number of nodes? Now, if I say what are the number of nodes, if I am here, it is very easy to define the number of nodes on LHS. Right? What are the number of nodes on LHS? 3. Plus the number of nodes on RHS. What are the number of nodes on RHS? 1, 3 plus 1 is 4. Plus the node itself. Therefore, what is the answer? 1 plus the number of nodes on LHS plus the number of nodes on RHS. That is what I have to compute now. Therefore, we say int L is equal to count nodes on LHS. Therefore, I say root arrow left. Now in case of height we have taken maximum. Here I don't take maximum, I add it. Now next, the number of nodes on RHS. Therefore how do I write it? Count nodes of root arrow right. Right. Now L is the number of nodes on LHS. R is the number of nodes on RHS. What is the final answer? Final answer is the number of nodes on LHS plus the number of nodes on RHS plus the node itself. Therefore I say plus 1. Now, let us trace it. This will be line number 1, 2, 3, 4, 5. Right. Now, we have called one function called as count. I just say count of root. What is the value of root? 25. Again, there are two variables, left and the variable is right. Is 25 equal null? No, you call the function again count on root arrow left. 25 arrow left is 10, and we are calling this from line number 3. Again there are two variables left and right. Go back. 10 equal null? No, again you call the function count of 10 arrow left. What is 10 arrow left? 7. Return line number is 3. Again there are two variables left and right. Go back. Is 7 equal null? No. Again you call the function count of 7 arrow left. What is 7 arrow left? Null, and the return line number is 3. Now, is null equal null? Yes, return 0. You return 0. Where do you return 0? To line number 3. And what does line number 3 says? L is equal to 0. That means the number of nodes with respect to 7 on LHS are 0. Now you count the number of nodes with respect to 7 on RHS. Count of 7 arrow right. What is 7 arrow right? Null, and we are calling this from line number 4. Null equal null? Yes, return 0. Where do you return 0? To line number 4. Therefore you say R equal to 0. It means what? With respect to 7, the number of nodes on RHS are 0. Next, execute line number 5. Return L plus R plus 1. What is L? 0. What is R? 0. 0 plus 0 is 0. 0 plus 1 is 1. You return 1. Where do you return 1? To line number 3. Therefore L equal to 1. And what does it say? The number of nodes with respect to 10 on LHS are 1. Now you have to count the number of nodes with respect to RHS. You say count of 10 arrow right. What is 10 arrow right? 11, and we call this from line number 4. Again there are two variables, L equal to R equal to. Now is 11 equal null? No. Execute line number 3. Count of 11 arrow left. What is 11 arrow left? Null. And we have called this from line number 3. Is null equal null? Yes, you return 0. Where do you return 0? To line number 3. It means the number of nodes with respect to 11 on LHS are 0. Now you execute line number 4. Count of 11 arrow right. What is 11 arrow right? Null. The return line number is 4. Null equal null. Yes, you return 0. Where do you return 0? Line number 4. It becomes 0. That means the number of nodes with respect to 11 on RHS are 0. Execute line number 5. Return L plus R plus 1. 0 plus 0 is 0. 0 plus 1 is 1. It returns 1. Where does it returns 1? To line number 4, and it says R equal to 1. That means the number of nodes with respect to 10 on RHS are 1. Now, execute line number 5. Return L plus R plus 1. 1 plus 1 plus 1. It is what? 3. It returns 3 to where? Line number 3. Therefore, it becomes L equal to 3. And it says the number of nodes with respect to 25 on LHS are 3. Now, execute line number 4. Now, what is line number 4? Count of 25 arrow right. That is 37, and the return line number is 4. This is L and this is R. Now, is 37 equal null? No. Again you execute line number 3. You say count of 37 arrow left. It is null. Return line number is 3. Is null equal null? Yes. It returns 0. Where does it return 0? To line number 3. It means the number of nodes with respect to LHS on 37 are 0. Now you execute line number 4. You say count of 37 arrow right, which is null. Return line number is 4. Null equal null? Yes. It again returns 0. Where does it return 0? To line number 4, and it says R equal to 0. The number of nodes on RHS of 37 are 0. Now execute line number 5. Return L plus R plus 1. Return 0 plus 0 plus 1. What is it? 1. Therefore, the value of R here will become 1. Now, line number 4 is done. Execute line number 5. Return L plus R plus 1. 3 plus 1 plus 1. 3 plus 1 plus 1 is 5. And it returns 5. The number of nodes are here what? 5. This is how we count the number of nodes in a binary tree. What is it? It's very simple. The number of nodes on LHS plus the number of nodes on RHS plus the node itself. Right. Now let us see how do we count the number of leaf nodes. Now what are the leaf nodes over here? 7, 11 and 37. That means 3 should be the answer over here. Let's see how to do it. Thank you. Now let us see how do we count the number of leaf nodes. That's the case 8. I say case 8. Now what are the number of leaf nodes? It can be 1, 2, 100, anything. Let us say y is equal to count leaf. We will write one function, and I say root, and you print the value of y. That's the end of the case 8. Now how do we write the function? We say int What is the function name? Count leaf. What is the first parameter? Struct node star root. Now, if suppose again the value of root is null. Now tree itself is not there. How do you come the leaf nodes? That's the base condition. We say if the value of root is equal null, that means there are no leaf nodes and we return 0. Now, how do we count the leaf nodes? Very simple. Leaf nodes are nothing but with respect to 25. How many number of leaf nodes are there on LHS? 2. How many number of leaf nodes are there on RHS? 1. 2 plus 1. That means the number of leaf nodes on LHS plus the number of leaf nodes on RHS. Now the question comes, how do we know that it is a leaf node? How do we know that it is a leaf node? If there is no left child and there is no right child. Suppose I write 10 over here and I say null and null. The left child is null and the right child is null. Such a node is called as what? The leaf node. It means if root arrow left is equal null and what should be the other condition? Root arrow right should also be equal to what? Null. That means if the left child is null and the right child is null, it is a leaf node. And if it is a leaf node, what I have to do? I have to return 1 because I have encountered one leaf node over there. Now, then you have to count the number of leaf nodes on LHS. Therefore, we say int L is equal to count the number of leaf nodes on LHS. And then we write count the number of leaf nodes on RHS. And what is the final answer? The final answer is the number of leaf nodes on LHS plus the number of leaf nodes on RHS. Now let's trace it. Let this be line number 1, 2, 3, 4, 5, 6, 7. Okay, let this be the tree. Now again I say count leaf. I just write it here, count of 25. There are two variables L and R. Is root equal to null? No. Root arrow left, is 25 arrow left equal null? No. You execute line number 5. You say count of root arrow left, that is 10, and the return line number is 5. And again there are two variables L and R. Is 10 equal to null? No. Is 10 arrow left equal to null? No. Again you execute line number 5. You say count of 7 and the return line number is 5. Is 7 equal to null? No. 7 arrow left is equal to null? Yes. 7 arrow right is equal to null? Yes. That means it is a leaf node. Therefore you return 1. That means one leaf node is found. Where do you return 1? To line number 5. That means with respect to 10, the number of leaf nodes on LHS are 1. Next you need to find the number of leaf nodes on RHS. Therefore you say count of 10 arrow right. What is 10 arrow right? 11, and the return line number is 6. Now, is 11 equal to 0? No. 11 arrow left equal to null? Yes. 11 arrow right equal to null? Yes. Therefore, you return 1. Where do you return 1? To line number 6. Therefore, R becomes 1. Execute line number 7. Return L plus R. Return 1 plus 1. What is 1 plus 1? 2. And where do you return to? To line number 5 of this. Therefore, with respect to LHS, the number of leaf nodes are what? 2 on 25. Now, you have to see number of, now execute line number 6. And what does line number 6 says? Count of root arrow right. 25 arrow right is what? 37. And you call this from line number 6. Is 37 equal to null? No. 37 arrow left equal to null? Yes. 37 arrow right equal to null? Yes. You return 1. Where do you return 1? To line number 6. And R becomes 1. That means the number of leaf nodes with respect to 25 on RHS are 1. Execute line number 7. Return L plus R. Return 1 plus 2. And what is 1 plus 2? 3, and 3 is the number of leaf nodes. Now let us see how do we delete a binary tree, and that will complete our course on the binary search tree. Thank you. Let us see how do we delete this tree. I said the question on trees can be done with any of the tree traversals. Now let us try to do pre-order traversal over here. Now what is pre-order traversal? First root should be executed. Now if I delete this 25, first root should be deleted, right? 25. Can I go on the left tree and right tree? I cannot go. Therefore, pre-order traversal cannot be used over here. Right. Now next the question comes, can I use the in-order traversal of the tree? In-order traversal means what? First you go to 10. Now if I delete 10, can I go to 11 over here? No, because it is lost. The link is lost. Therefore, you cannot use in order traversal over here. Next, the question comes, can I use post order traversal of the tree? Now, what is post order traversal of the tree? Left, right, root. Now, in this case, what is post order traversal? If I write, it is 11, 10, 37, 25. This is the post order traversal. Now, if I delete 11, do I lose any pointer? No. If I delete 10, do I lose any pointer? No. If I delete 37, do I lose any pointer? No. At last, if I delete 25, that's it. Therefore, the deletion of the tree has to be done with post order traversal. Now, the question comes, can we use the level order traversal over here? Yes, you can use the level order traversal, because level order traversal means you use queue. That means you store address of 25. Right. Next you store 10 and 37. Now when I dequeue it, I delete 25 as well. Now if I delete 25, can I go to 10 and 37? Yes, because they are available in queue. Therefore, level order traversal can also be used to delete a binary tree. Right. But let me use the post order traversal of the tree and help you how do you delete the binary tree. Now how do you delete it? You say void. We will write one function called as delete tree, and what do we need? We need the root of the binary tree. Now, if the root is already empty, that means root is already null, can we delete it? No, therefore I say if root is not equal to null, then only you delete it. If root is null, nothing to be deleted. If root is null, null not equal, null is false, do not execute this. Closing bracket is taken as return, nothing to be done. Now, this delete tree has to be done in what fashion? Post order fashion. Therefore, what do I write over here? I say delete tree. What is post order? First you go on the LHS. Then we go on the RHS. Then at last what we do? We process the root. How do we process the root? We will see it in some time. Suppose this is what I have written. I am missing one line. I will execute this. Now we say delete tree of root. What is the value of root? That I have taken it to be 25. Okay. Now is 25 not equal to null? Yes. You execute line number 1. Delete tree of root arrow left. Now what is root arrow left? It is 10. And from which line number we are calling? From line number 1. Now again go back. 10 not equal to null? Yes. Again you execute 10 arrow left. Delete tree of 10 arrow left is null and the return line number is 1. Go back. Null not equal null is false. You come out. Line number 4 is executed. It means return. Where to return? Line number 1. Completed. You have to execute line number 2. And what does line number 2 says? Delete tree of 10 arrow right, which is 11, and we are calling this from line number 2. 11 not equal to null? Yes. Again you have to go on LHS of this. We say delete tree of 11 arrow left. It is null and the return line number is 1. Null not equal null is false. You come out, execute line number 4, which says return. Now where to return? Line number 1. Execute line number 2. Delete tree of root arrow right. Now what is 11 arrow right? 11 arrow right is null and the return line number is 2. Null not equal null is false. Again you execute line number 4. You return. Where to return? Line number 2. Done. Now LHS tree is deleted. RHS tree is deleted. Now this 11 should go. And what do I write over here? I say free root. Now, what is the value of root over here? 11. That means the address of it. And this is being deleted. Right. Now, again you execute line number 4. It means return back. Where to return? Line number 2. Nothing to be done. Execute line number 3. Free root. Free 10. Free 10. Done. Now, execute line number 4, which says return. Where to return? Line number 1. Done. With respect to LHS, all are deleted. Now, you have to delete with respect to RHS. We say delete tree of 25 arrow right, which is 37, and the return line number is 2. 37 not equal to null, yes. Again you say delete tree of 37 arrow left. That is null, return line number is 1. Null not equal null is false. Execute line number 4, which says return. Now again you say delete tree of 37 arrow right, which is null. Null not equal null is false. Again you say return. Where to return? Line number 2. Done. Now you have to execute line number 3. Free root. What is free root? Free 37. Free 37. Gone. Now you execute line number 4. Again it says return. Where to return? Line number 2. Done. Execute line number 3. Free root. Free Root, what is root 25? Free it. Now execute line number 4, which says return, and you see that the complete root is being what? Complete tree is being what? Deleted. This is how we delete the node from the binary tree. We use the post order traversal. Delete root is always done using post order or level order, and I said why in order or pre-order doesn't work over there. And this completes the chapter for the binary trees, and in the next video I will start with the missed chapter that we did on files. Okay, thank you.